Hello, today I'll be talking about palladium-catalyzed vinylic hydrogen substitution reactions with Aryl, Benzyl, and Styryl halides. This journal was by Richard F. Heck and J.P. Nolly Jr. My name is Kyle Oswald, and I will be presenting this information to you today. So just a bit about the author himself, Richard F. Heck. He was born on August 15th, 1931 in Springfield, Massachusetts. He is the American chemist noted for discovery and development of the Heck reaction, which we all should know that uses palladium to catalyze organic chemical reactions that couple aryl halides with alkenes. An example of a compound that is prepared industrially using the Heck reaction is an analgesic naproxen, which basically is just a painkiller. He got his education from the University of California, Los Angeles, UCLA. He published this journal in 1972 when he was at the University of Delaware, and in 2010 he won the Nobel Prize in Chemistry for the Heck reaction. In the picture below is shown a schematic of the palladium-catalyzed reaction that Heck has developed. So, an overview of what I'll be talking about today, just some background information about the topic, simple things about the Heck reaction. I'm going to be talking about Tomuzu Masaroki's work, which is work that Heck based his research on. Then we got the main author, Richard Heck's work, that I'll be going more detail of what his results were. And then I'll be presenting Akira Suzuki's work, which is work after the Heck reaction. So Suzuki's work was essentially basing Heck's work, but with what he wanted to work with. I'll go into more detail about that later as well. Then after I discuss the three works, I will be comparing between all three reactions. And then I'll be talking about these types of reaction in today's world. So next I'll be talking about some background information about the paper, some terminology. I'll be discussing an olefin is any class of unsaturation open chain hydrocarbons having at least one double bond. An aryl halide is an aromatic compound in which one or more hydrogen atoms directly bonded to an aromatic ring are replaced by an halide. And benzyl halides is an alkyl halide in whose molecule there are one or more halogen atoms on the benzylic carbons. So, background about the general paper itself. Tomuzu Masaroki and his group developed a method for hydrogen substitution reactions with aryl, benzyl, and Styryl halides for olefinic compounds. In Masaroki's paper, it was discussed that he did this reaction, this palladium catalyzed reaction, under not so standard laboratory conditions. He was at high temperatures, around 150 degrees, and he was only using certain molecules. He just wasn't using as many molecules. So what Heck's group and what Heck wanted to do was to somehow run this reaction under more standard laboratory conditions, along with adding more molecules to this reaction to see if we can broaden the field, to see if there's more compounds we can react in order to form more of this type reaction, more products out of this reaction. So, like I mentioned before, I'm going to be talking about Tomuzu Masaroki's paper. His group, we all know his group was developed the method for hydrogen substitution reactions with aryl, benzyl, and Styryl halides for olefinic compounds. There wasn't really much information given from Heck's paper. It just discussed that how he was running this reaction under non-standard laboratory conditions. Like I said before, high temperatures, not so many molecules, and just wanted to see if this reaction would work. This palladium catalyzed reaction would work, which it did, and it's still a major discovery today in the chemistry world. But it's unfortunate that I could not find the paper on this to give you more information. But that being said, Heck based his paper off of this man in this work, so I can provide more information about these palladium-catalyzed reactions. So Masaroki's results have shown that him and his coworkers have reported a palladium-catalyzed arylation reaction with olefinic compounds with aryl iodides and potassium acetate and methanol at 120. Heck's paper also discussed that they also did the same thing, but only at 150 degrees. So Masaroki also was using temperature ranges from 120 to 150, which is pretty high temperature. The reaction is undoubtedly closely related to the known olefinic arylations and alkylations achieved at room temperature or below with palladium salts. So even though it was achieved at room temperature or below with palladium salts, the catalyst wasn't used at this low temperature. It was similar, but it just wasn't used. So what Heck's group wanted to do was to see if they could do Masaroki's work, the palladium-catalyzed reaction, but only at a lower temperature, more standard laboratory conditions. So Heck's results shown that the well-known catalysts, the PDP-C6H534, reacts readily with a variety of organic halides to form an oxidated addition products of the type with the substrate and the catalyst form. When prepared in the presence of an olefinic compound, these organoplatinum halides undergo an addition reaction with the olefin, and then the adduct decomposes by eliminating essentially the palladium halide, forming the substitute olefinic compound. And as you can see here below, this particular reaction is from Richard Heck himself, the journal he produced in 1972. And as you can see, it doesn't show arrow pushing, but it shows how the reaction took place and what types of catalysts they use along with the olefin they use to get out a product that that you can get the R group. You can get this R group on the olefin rather than this hydrogen group from the beginning. So right then and there, we all know that that's a pretty big advancement in the chemistry world, because Masaroki's group did it at high temperatures, Heck's did it at low temperature. So it is shown, Heck's results shown the different types of organic halides you use with the compound, reaction time, the product with percent yield, and the melting point of the product. This table comes directly from Heck's paper. So as you can see right here, the organic halide they use a lot of iodobenzenes. They strictly used for the first part of the organic halides. The majority of them use iodine or iodine, and then the last two, one uses a chloride and one uses a bromine substituent. So right here, the next one right here is the compound, the olefinic compound they use. So they used some styrene, some methyl acrylate, some propene, and just different types of styrene. I would mention, and I would say, in my opinion, this right here is the most important part of this table. And I say that because it is the reaction time at 100 degrees per hour, the reaction time at 100 degrees, and the number shown is how long it took in hours. And the reason I say it's the most important is because it is at 100 degrees. We know Masaroki's group did it at 120 to 150, so already we're lowering the temperature, and Heck just wanted to see if reactions would take place. So as you can see, the reaction did take place. The first couple took 2 hours, one took 1 hour, one took 5, but towards the bottom, it seemed to be getting a little longer, taking a little longer, 15, 72 hours, and I'll discuss that later, why these took so long, but just the fact that this reaction time that this reaction happened at 100 degrees is just already an advancement compared to Masaroki's group. And next, I would like to discuss the products. They did form products with these with percent yields. And the percent yields, even though they ranged, they still formed a product, which, like I said, is a huge advancement given the temperature of this reaction. And then lastly, they had the melting point of each product. And even though some melting points weren't recorded or weren't found, they still had some to base their information off of, which is good. So Heck's overall results shown that there were 3 types of halides formed when this reaction took place, and that was the aryl, the benzyl, and the Styryl. In the aryl example, only the iodides reacted rapidly. Some product formed with the bromobenzene, but the reaction was very slow, even at 150 degrees. And the benzyl chloride and the beta bromostyrene were less reactive than the aryl iodides, but they gave reasonable yield with longer reaction times. So even if the reaction took longer, the percent yield was higher. So their overall results were better when the reaction took longer. But in the aryl example, they reacted rapidly, so they did have some fast reactions. Some products formed very fast, but they also had the problem with very slow reactions, even at a greater temperature. For the Styryl halides, Heck's paper mentions the Styryl halides in the results, but he doesn't give an example of the Styryl halides in the results. I think he did not put this in his paper because I think the results of the Styryl halides, the yields might have been too low to account for, or the reaction took too long to be considered a no reaction process, like if the reaction just had no reaction. To continue with Heck's results, as with reactions employing organomercury compounds, these reactions tolerate a variety of functional groups, such as nitro-methoxyl and carbomethoxyl. Relatively low yields are obtained with olefinic compounds having a methylene group adjacent to the double bond. So the first bullet point, there's different groups when this reaction took place, such as the 3 I listed. And this happens because of what the halide was reacting with the olefinic compound produced a product at a certain temperature and at a certain rate, as the table shown in previous slides. And then the relatively low yield that were attained with the compounds with the methylene group adjacent to the double bond. Heck did not really go into detail about why they had low yields. I am predicting that it had to do with the dipole-dipole moment of each of the carbons attached to the different types of bonding dealing with those groups. So to continue the discussion with Heck's discussion, this new vinylic substitution reaction is clearly an improvement over the mercurial reaction in many instances, particularly for preparing larger quantities of a material. It does have some limitations, however, which the mercurial method does not have. The loss of stereochemistry in certain molecules. Other limitations include not being able to use a base-sensitive compound such as aracilin in the reaction and not being able to methylate by the halide reaction. So Heck did find a better way to do this on a larger quantity scale, which means we can do it at more standard laboratory conditions. Even though it does have some limitations, it's still a huge advancement. The loss of stereochemistry might come to effect if a scientist or a chemist is trying to get a certain type of stereochem with this palladium-catalyzed reaction, and not using base-sensitive compounds and not be able to methylate by the halide reaction. When they did that, it said that the product they wanted to form was not the right product they wanted, so they just eliminated trying to do that in general to see if it would work, and it did. So that's why it's a limitation. You can't do it. Another limitation is higher temperatures of the halide reaction. The double bond migration looks set to be more serious, and the corresponding reaction with the benzyl mercurate acetate and the palladium acetate at room temperature gave only the expected trans-methyl-4-phenyl to butanate. At higher temperatures, the halide reaction shown double bond migration to be more serious. So if Heck wanted to have the double bond in a certain area, or didn't need to move around, or didn't want the double bond to move around or force somewhere else, he had to see what certain temperature, probably lower temperatures, to see if the double bond would stay where he wanted it to stay. And as the schematic shows below with the reaction, he ran it at a certain temperature where the double bond stayed where he wanted it to stay, which it did work, but it did only give one type of stereochem, which is trans, which was expected because that was one of the limitations, was the stereochemistry of this reaction running it at room temperatures. So some future works that were based off of Heck's reaction was Arika Suzuki's paper. He and his group developed the way to find stereospecific cross-coupling by palladium-catalyzed reactions of one alkyl boranes with one alkyl or one alkaline halides. So even though Heck's paper was produced / published in 1972, Suzuki's paper was published a couple years later, basing his reaction off of Heck's reaction. He used very similar techniques and very similar methods that Heck used to hopefully further advance the development of his research. And he actually has a reaction named after him, the Suzuki reaction. So an overall summary of Suzuki's work was the representative E1 alkenyl diamyl boranes and E1 alkenyl 132 benzodioxyl borols readily attainable via hydroboration of one alkynes react with one alkenyl halides or one alkynyl halides in the presence of a catalytic amount of tetracous palladium and base to give corresponding conjugated E-dienes or E-imines with high regio or stereospecificity in good yields respectively. So some similarities and differences between the first two papers I talked about. The first paper I talked about was Masaroki, and we all know that his group developed a method for hydrogen substitution reactions with Aryl, benzyl, and Styryl halides for olefinic compounds. And it is similar to Heck's paper because Heck based his research in this paper on Masaroki's initial research. So he just wanted to try to better the reaction that was presented before him. Masaroki, however, ran the reaction at not so standard laboratory conditions and only had unlimited compounds to use. And he did this because he just wanted to see if the reaction would take place, if the reaction would occur. And he was successful in this experiment, but the conditions were just not standard. So what Heck wanted to do is he wanted to make it more standard. Like I said before, he ran it at lower temperature. He ran it around 100 degrees rather than Masaroki's group running it to about 120 to 150 degrees. And he used more compounds. Even though Heck's reaction did happen, it did occur, there were some limitations. Like you couldn't use base-sensitive materials, only one type of stereochemistry formed, etc., etc. So some similarities and differences between Heck and Suzuki. Heck's paper was published before Suzuki's paper. So we all know that Heck used used a developmental method for hydrogen substitution reaction with Aryl, Benzyl, and Styryl halides for olefinic compounds. This paper was the starting point for most research dealing with palladium-catalyzed reactions with organic compounds. Suzuki did base his research off of Heck's initial research reaction. He based it off of the palladium-catalyzed reaction. But Suzuki used different compounds and different substrates dealing with palladium and a base to give the corresponding conjugated dienes or ions with higher regio or stereospecificity and good yields respectively. So like I said before, Heck had some compounds with high yields, he had others with low yields. His was just mix match error in data. Like we could assume that the higher yields presented lower error, but the lower yields presented higher error. But with Suzuki, he found a way to use the palladium catalyzed reaction with different substrates and different molecules to give better yields and better regiospecificity and stereospecificity. So he basically advanced Heck's paper farther than Heck did, which is good. So now here are some applications that use the Heck's reaction in today's world. Bioorganic chemistry and organic chemistry are the main two that really use the Heck's reaction in today's world. For organic chemistry, a palladium-catalyzed defunctionalization of enol ethers to amino acetyls with amyls and alcohols. And for bioorganic chemistry, they use the Heck reaction to synthesize some biological material to resist leukemia cells. So basically, these two different chemistry types of chemistry are using it to try to better the world today. As you can see, for bioorganic chemistry, they are trying to figure out a way to develop a method with Heck's reactions to be resistant to leukemia cells, which is great, which can help further research for cancer and other types of biological research dealing with leukemia cells. In organic chemistry, they are finding a way to defunctionalize enol ethers to amino acetyls. So that can also further research and further development of particular reactions dealing with this type of organic chemistry. And like I mentioned before, the application of the N-acetylic naproxen is a painkiller. So they actually use the palladium catalyzed reaction to form painkillers in medicine in today's world, which is huge because with the advancement of medicine and technology, we just need to try to find a way to be resistant to different types of viruses and diseases. So in conclusion, in an overall summary, we learned that Masaroki and his co-workers reported a palladium-catalyzed reaction of aliphatic compounds with iodides and potassium acetate in a solvent at 120. It was also reported at 150. We all know the well-known catalysts that Heck used to form reacts readily with a variety of organic halides to form an oxidative addition products of the type of the catalyst with the new product. And palladium and base give corresponding conjugated E-dienes or E-iones with high regio and stereospecificity and good yields respectively. And we also know that Heck's reaction did, however, work. There was just limitations to it that at the time were not that major because he figured out a way how to have the original reaction occur at lower temperatures under standard laboratory conditions and can be made by many companies industrially. So that is why his overall process and his overall development of this reaction is called the Hecht reaction. Here are the references I used for this presentation. As you can see, there are 21 total with a variety of different types of papers. And lastly, I would like to thank you for watching my presentation on palladium-catalyzed reactions by Hecht. And I hope you guys all enjoy this. If you guys have any questions or comments, please comment below, and hopefully I can get back to you and be able to answer them to the best of my ability. Once again, thank you for watching.